Hi, this is Andrea Hendricks, and today's lesson is solving systems of equations by the addition method, which is also called the elimination method. Our goal in this section is to add the two equations in the system so that one of the variables is eliminated. I should add one other thing is that the equations have to be in the same form. That is usually the form ax plus by equals c, the standard form. But just to review, what does it mean for variables to be eliminated? That is when we add them, they add to 0, like negative 5x plus 5x adds to 0, or 2x and negative 2x add to 0. So what we're really requiring is that the coefficients of the variable must be opposites. Sometimes you will be given that form in the system. If not, your only allowable operation is that you can multiply one or both of the equations in the system by a non-zero number to get the equations in the form in which one of the variables has opposites as coefficients. It's not as hard as it sounds. So let me show you some examples. Like this system, 2x plus y equals 6 and 3x minus y equals 4. If we examine the coefficients of x, 2 and 3 are not opposites of one another, but the coefficients of y are opposite, right? This is a positive 1, this is negative 1, so they're opposites. So we can actually go ahead and add those two equations together to get 2x plus 3x is 5x. The y and minus y add to 0, and that's equal to 10. And our whole goal is that we get an equation with one variable that we can solve. So when we divide through by 5, we find that x is 2. And now we have to do just like we did with other methods, we have to find the corresponding component of the ordered pair that satisfies those two equations. So we have to substitute in the 2. So we have to, at this point, solve for y. And so we would have 2 times 2 plus y is equal to 6, and I could certainly use either one of those equations. So that's 4 plus y is equal to 6. Subtracting 4 gives us y is equal to 2. So our solution is the ordered pair 2, 2. And remember how we can check that. By plugging in 2 times 2 is 4, plus 2 is 6. 3 times 2 is 6, minus 2 is 4. So it satisfies both equations, so we know we've done it correctly. Now, let's look at one where we have to do some work to get them in the same form. 2y equals negative 3x, and negative 3x minus y equals 3. So the first thing we need to do is rewrite them so that x and y are on one side. So in the first equation, we can actually add 3x to get 3x plus 2y equals 0. And the second equation stays the same. And in rewriting, notice that the coefficients of x are opposite, right? A 3 and a negative 3, those are opposites of one another, so we don't have to do any work to change the equations. We can just simply add them. So 3x minus 3x is 0. 2y plus a negative y is 1y is equal to 3. So now we need to solve for x. So we can plug that into either one of the equations. It doesn't matter. So if we plug into the first equation, we would have 2 times 3 is equal to negative 3x. 6 equals negative 3x. And we can divide by negative 3 to get x is equal to negative 2. So our solution to this system is the ordered pair negative 2, 3. And we can certainly plug that in, right? Negative 3 times negative 2 is positive 6, minus 3 is 3. 2 times 3 is 6, and that is equal to negative 3 times negative 2, which is 6. So it checks in both equations. Let's look at an example where we have to do some work to one of the equations. 2x and 3x. And 1 and 2. Neither one of those pairs of coefficients are opposites. So we have to multiply one or both of the equations by some number, depending on which variable we want to eliminate. So let's say that we want to eliminate the y. And you could choose to eliminate x. It doesn't really matter. But what we have to do is examine the coefficients. We have a negative 1 and a 2. What we have to do there is find a number that both 1 and 2 divide into. and 1 and 2, it's really like finding the least common denominator. 1 and 2 both divide into the number 2. So what we need is that one equation has a coefficient of positive 2 and one has a coefficient of negative 2. Well, see, we already have the positive 2, so we can leave the second equation unchanged, but we need to do something to the first equation to get a negative 2 in that place. So since its coefficient is negative 1, what we can do to figure that out is say negative 2, which is what we need there, divided by the existing coefficient, which is negative 1, and negative 2 divided by negative 1 is positive 2. So if we multiply the first equation by positive 2, we'll get our system in the form we need to add. So we would have 4x minus 2y is equal to 24. So all I'm doing is distributing the 2 to every part of the equation. The second equation stays the same. And now we can add the two equations together. So if we add them, we get 7x, the y's are eliminated, is equal to 21. Dividing by 7, we get x is equal to 3. And now we can solve for y. Doesn't matter which equation we use. If I use the second equation, I'd have 3 times 3 plus 2y equals negative 3. 3 times 3 is 9, plus 2y equals negative 3. So we can subtract 9 from both sides to get 2y is equal to negative 12, and divide by 2 to get y is equal to negative 6. So our solution is the ordered pair, 3, negative 6. Now I can check, right? 2 times 3 is 6. Minus a negative 6 is positive 6, which equals 12. 3 times 2 is 6. Plus 2 times negative 6. I'm sorry. 3 times 3 is 9. Plus 2 times negative 6 is negative 12. And 9 minus 12 is negative 3. So that solution checks. Okay? Let's look at this system. 3x plus 3y equals 33, and 5x minus 2y equals 27. So here again we have to make a decision. Which one do we want to eliminate? This time I'll say let's eliminate the x. Well, if I look at and again what I realize is that none of those were opposites initially. If they were, I could just add them and go on. But since they're not opposites, I need to do some multiplication. If I want to eliminate the x, I've got to find a number that both 3 and 5 go into. And 3 and 5 both divide into 15. So I need one equation to have a positive 15 and one to have a negative 15, and it doesn't matter which one. So if I make the first equation a positive 15, I say 3 goes into positive 15 5 times. So that's my multiplier there. To make the second equation negative 15, I have to say 5 goes into negative 15 a negative 3 times. Okay, so did you see what I did? 15 divided by the coefficient of x, which is 5, and then negative 15 divided by the coefficient of x in the second equation is negative 3. So that's how I determine what I need to multiply by. So when I multiply, I get this new system. That is 15x plus 15y is equal to 33 times 5, which is 165. If I multiply the second equation through by negative 3, I get negative 15x plus 6y. Be careful with the signs. A negative 3 times negative 2 is positive 6y. And then a negative 3 times 27 is a negative 81. Okay? So now I have opposites on my coefficient, so I can add the two equations. Upon adding, my x's are eliminated, and I get 15y plus 6y is 21y is equal to 165 minus 81, which is 84. And then if we divide both sides by 21, we get y is equal to 4. So now we need to solve for x. So to solve for x, I'm going to replace the variable y with 4 in either one of those equations. It doesn't matter which one. So I'll just choose the top equation. So if we have 3x plus 3 times 4 is equal to 33. So 3x plus 12 is equal to 33. And we can subtract 12 from both sides to get 3x is equal to, what is that, 21. So therefore, our x is equal to 7. So this says that our solution to this system is the ordered pair 7, 4. And I can certainly plug in to check to see that that works. Let's look at negative x plus 3y equals 4 and negative 2x plus 6y equals 8. So here again I have to make a decision. Which one do I want to eliminate? Let's go for eliminating the y's. So if I have a 3 and a 6 as coefficients, what number do both 3 and 6 divide into? Well, they both go into 6. Well, I already have a positive 6, so I don't need to do anything with that. But I do need to get this negative 6. So to get a negative 6, I've got to divide negative 6 by the other coefficient, which is 3. And negative 6 divided by 3 is negative 2. So I need to multiply the first equation by negative 2. And in doing that, I'm going to distribute to all the terms. So negative 2 times negative x is positive 2x. Negative 2 times 3 is negative 6y. And negative 2 times 4 is negative 8. And my second equation remains the same. Now notice something interesting that happens here. My x's are eliminated and my y's. So I get a 0 is equal to 0. And this kind of looks like what happened with substitution. If this is a true statement and the variables are gone, what this is really telling me is that those two lines are the same. And so this is a case where there are infinitely many solutions. So remember how to write our solution set. We would say it's a set of all ordered pairs such that it satisfies one of the equations. Well, they're the same, so you can just put either one in here. Okay? So that's one of the special cases. We're still going to see either a unique point, no solutions, or infinitely many solutions. And my last example will illustrate the no solution. If I have 5x minus 2y equals 3 and 10x minus 4y equals 5, let's choose this time to eliminate the x. So if I have a 5 and 10 as coefficients of my x, what number do both 5 and 10 divide into? Well, that is 10. So I need one to have a positive 10 as a coefficient, one to have a negative 10. We already have the positive 10, so I need a negative 10 on the first equation. If I divide negative 10 by 5, it tells me that I need to multiply by negative 2. So in doing that, I get a negative 10x. Negative 2 times negative 2y is a plus 4y. Negative 2 times 3 is a negative 6. And my second equation stays the same. So notice what happens in this case when I add the two equations together. My x's are eliminated and my y's, so I get 0. But negative 6 plus 5 is a negative 1. So in this case, I get a false statement, which tells me that these lines are parallel and that there is no solution to the system. Okay? So this is how you use elimination or the addition method to solve systems. If you have any questions, please don't hesitate to contact me. Thank you.